Last lecture, we focused mostly on correlational design. And so this chapter, we're going to move on to talking about the experimental methods and using experiments to study causal relationships. When we analyze experimental designs, and I'll focus mostly on the analysis in this lecture, but of course the rest of the content is in your book. There are three general steps to analyzing experimental designs. First, you check the data. You're looking for errors or outliers, things like that. Then you describe the results and summarize the data. So this includes means, standard deviations, graphing to get a sense of generally what the data looks like. And then finally, you do what's called inferential statistics to confirm what the data reveal. So in terms of descriptive statistics, the mean, in general, we're not interested in an individual score, but how people respond on average to each condition. So there are multiple measures of central tendency, which is kind of, can you give a single score that represents the center of the distribution? The most commonly used one is the mean, which is the arithmetic average for each condition. So generally what you do is, especially if you're doing an experimental design where you have an independent variable, maybe you have a control or experimental group, you want to know what the mean score is for the people in the control group and the people in the experimental group to look at if there is a difference between them. So the mean gives you that measure of central tendency, that central score, but we know that not everyone responds in the same way to each condition. And so that's why we look at the standard deviation. So what a deviation is really how far a score is from the mean. So a standard deviation is the average of everyone's distance from the mean. So this data is looking at a study that looked at how many hours of sleep students get in early classes, 9 a.m. versus later classes, 11 a.m. And so when you look at this study, at this data, you'll notice that the mean is actually identical. But you can also see that the range for the 11 a.m. class is much bigger. The scores are more spread out, right? You go from 0 to 13 in 11 a.m., whereas in the 9 a.m. class, people get between 3 and 9 hours of sleep. And so the standard deviation is trying to capture that distance from the mean. Another descriptive statistic you might use is the effect size. So the effect size has to do with how large of an effect does the independent variable have on the dependent variable. With the effect size, you're kind of ignoring the signs and you're just going to look at the value. And the most commonly used effect size is Cohen's d. And so here what you're doing is you're comparing the treatment mean minus the control mean. So you're comparing the two means and dividing by the standard deviation. So if the average for the 9 a.m. class is 6 and the average for the 11 a.m. class is 6.5, the question is that a big difference or a small difference? But you need to take into account that standard deviation. And by dividing by the standard deviation, it gives you a standardized measure and helps you kind of designate small, medium, or large. Okay. So these are some kind of rough guidelines for interpreting Cohen's d. Or the effect size. So a small effect size is a d of less than about 0.2. A medium effect size would be between 0.2 and 0.8, and a large effect size would really be greater than 0.8. These aren't hard cutoffs, but these are kind of general guidelines. And then you also need to be able to kind of describe it in words. Okay, so you want to talk about how big of an effect size. So you might say something like the independent variable had a large or medium effect on the dependent variable. The second explanation is a little bit harder to do. So if your data fits that, then that's great. I think the first one is the simplest. So if we look at the 9 a.m. versus 11 a.m. class, we might say class time had a small effect on the hours of sleep. Okay, so we've got our independent variable, which is class time, and our dependent variable is how much sleep they got. And then we'd calculate out the Cohen's d and see how large of an effect it was. And so this is another example from the Schellenberg article. And so you can kind of take a look at, you've got the means for each group. So we've got the control group had an increase of 4.3, where the music group had an average increase in IQ of 7. So we can see that the music group is different, and it seems to be larger. And if you divide by the standard deviation, we just took the average of the standard deviation in this case. So that would give us 7.0 for the treatment mean minus 7.3, sorry, minus 4.3 for the control mean, divided by 7.3. We took the average standard deviation, the control group standard deviation. And that gives us a Cohen's d of 3.36, which is a medium effect size. And so we might say the music group had a reliably larger increase, a small to medium change in IQ. Or you might say music lessons had a medium effect on IQ score. Okay, so next, the descriptive statistics are really just trying to kind of describe what the data looks like. Inferential statistics are really trying to answer the question, did the independent variable actually lead to a difference in behavior? Descriptive statistics can kind of tell us trends, but it can't actually prove that. And so we're really trying to kind of confirm what the data reveals. So we're asking, does the independent variable produce a reliable effect on the dependent variable? How likely is it that your findings are due to chance rather than the independent variable? And then how likely is it that the sample mean differences are also present in the population? So if you find a difference between your groups in your sample, would you also find the same difference in the population? So one of the ways we try to get at this, would we find the same effect if we did a study in the whole population, is through confidence intervals. And so remember that your sample mean is an estimate of the population mean, right? The goal is always to be able to generalize to the population mean. And so what we can do is calculate these confidence intervals, which are a range of values that contain the true population mean with some probability. Normally it's 95%. So we want to be able to say that we are 95% certain that this range of values contains the population mean. So we're going to calculate this range based on our sample means. And the general thinking is, or the way we approach this is, we're going to take our sample mean and say, okay, we think this is our sample mean, and we are 95% certain that our population mean is going to be 2 standard deviations within the range of 2 standard deviations below our sample mean to 2 standard deviations above our sample mean. Okay, and that is our confidence interval. So let me show you a little bit about kind of what this looks like. So let's say we did a study. We had one group that had a mean of 57 in our sample and a second group that had a mean of 49 in our sample. Okay, and so we want to know, are they actually different? So we're going to look at our confidence intervals. And so when we take into account the standard deviation and calculate our confidence intervals, group 1 has a confidence interval of 54 to 60. Group 2 has a confidence interval of 45 to 53. So we are 95% sure that group 1's population mean is somewhere between 54 and 60. Likewise, we're 95% sure that group 2's population mean is somewhere between 45 and 53. So are these different? Would we find the same difference of group 1 being bigger in the population? So the way we do this is we look at whether these confidence intervals overlap. These ones do not. There's no overlap. So even if group 1 were as low as it could possibly be, and group 2 were as high as it could possibly be, there's still no overlap between them, which means it is very likely that in our population, group 1 would still be bigger than group 2. So what does this actually mean in terms of understanding our results? It suggests that our groups are significantly different, and it suggests that our independent variable had an effect on the dependent variable. So this is another example. What if it looked like this? Group 1's mean was 57, Group 2's mean was 53. Okay, so again, we want to know, would we find this same difference in the population? Now, when we add our confidence intervals, Group 1 ranges from 54 to 60, Group 2 ranges from 49 to 57. Notice that there's a lot of overlap here, right? It's possible that Group 1, the population mean, will actually be as low as 54, and Group 2's population mean could actually be as high as 57, so they could actually be swapped, and Group 2 could be higher than Group 1. So in this experiment, this means that the means are not different. We can't conclude that there's a definite difference or that we would see a similar difference in the population. So this tells us that the independent variable did not have an effect on the dependent variable. So when you are looking at confidence intervals, what you want to do is you want to compute the confidence interval around the sample mean in each condition. If the confidence intervals do not overlap, then we conclude that the population means for the conditions are different. Okay, so if the confidence intervals don't overlap, then the population means the groups are different. If the mean of one group lies within the interval for the other, if they do overlap, then the population means do not differ. We cannot be certain that our treatment had an effect. Okay. Another way that we test inferential statistics is what's called null hypothesis testing. And so the question is the mean difference between the conditions greater than what we would expect due to chance? Okay. And the way we approach this kind of test is we go in making the assumption that there are no effects. There's no difference between groups. And then we say, well, given the assumption that there is no difference, what is the likelihood of observing the result that we got? Okay, so if in reality, if we had a recording angel who knew everything and the reality was there was no difference between the groups, how likely is it that we would get the difference that we saw by chance? And the kind of conventionally accepted cutoff is if there's less than a 0.05 chance that you would get that difference just by random chance, then you can conclude that it wasn't random chance and there are in fact differences between the populations. So we're not going to go into a ton of detail on this. You're not really going to need to conduct your own null hypothesis tests. But you do need to kind of understand the 0.05 cutoff and what it means. So the null hypothesis is the starting point of this. And the null hypothesis is always that the population means for the groups are equal. That's not actually what you want to test. So the null hypothesis is not actually what you're interested in. It's the opposite of what you're interested in generally. So the null hypothesis for every experiment is no difference. So when you are null hypothesis testing, you assume that the null hypothesis is true. So if we take the Schellenberg example, we go through and we assume that music lessons, there's no difference between kids who get music lessons and kids who don't get music lessons on their IQ. The next thing you do is you use the sample means to estimate the population mean. Remember, you have the means from the sample of people who participated in your study, and you want to make assumptions about the population. So in the example, the mean IQ for kids with no lessons was 103, and the mean IQ for kids with music lessons was 111. So the difference that should be between lessons and no lessons was 8.1. So the question is the observed difference, 8.1, greater than what is expected when we assume the null hypothesis is true? Now, you don't need to be able to do these things. This is just kind of for your background knowledge. What you would do, and I'll give you these, is compute the appropriate inferential statistic. As far as we're going to get is the t-test. Okay, so this is the testing the difference between two sample means. And then you're going to identify the probability, the likelihood, the p-value associated with the inferential statistic. And this is the likelihood of getting the statistic given that the null hypothesis is true. You are going to compare that observed probability with a predetermined level of significance. It will always, for our examples, be 0.05, and almost all research it's 0.05. Okay, so you're comparing the observed probability that you got associated with your t-value with 0.05. If your observed p is bigger than 0.05, that means the size of that difference is relatively likely, given that there is no difference between the two groups. Then you do not reject the null hypothesis of no difference. So you conclude that the independent variable did not produce a reliable effect. So if you have a p greater than 0.05, there's no difference between the groups. In contrast, if you have a p-value of less than 0.05, you reject the null hypothesis of no difference, and you conclude that the independent variable did produce a reliable effect. So in the Schellenberg article, the null hypothesis was less than 0.05, so it was concluded that music lessons cause differences in IQ score. Now, it's important to note that this is all based on probability. And so we make errors, and we know that there's errors, and we actually kind of use those errors and can kind of guess the likelihood of these errors. And so we have kind of two scenarios. We've got the actual situation, right? What is true if you have a recording angel that knows the actual truth about whatever you're studying? The actual situation can be that there is, in fact, no difference between your groups, or that there is a difference between your groups and the effect does exist. And then we make these decisions, right? We make the decision to reject the null hypothesis, meaning that you assume that there is a difference between the groups, or you make a decision to retain the null hypothesis, meaning you say, well, I don't think there actually was a difference. So there's two ways that we can be right. One is that we can reject the null hypothesis and say there is a difference, and the actual situation is that the difference does exist. Or that we can retain the null hypothesis and say there is no difference, and in reality, there is no difference. But there's also two ways that we can be wrong. Type 1 error is the likelihood that we will reject the null hypothesis, so that we will say there is a difference when in fact there is no difference. Type 1 error is alpha. So we set that at 0.05. When we decide to say something is significant, we set that value and we say, we know that there's a 5% chance we could be wrong. We're saying there's a true effect, but maybe there's not. Type 2 error is the opposite mistake. So in type 2 error, we say that there is no difference, but in reality, there really isn't a difference. And so type 2 error is a little bit harder to calculate. So it's always important to kind of keep these in the back of your mind. I'd encourage you to make sure that you review this chapter in your textbook carefully, because there's a lot of additional information, but I tried to highlight in this kind of some of the key statistical parts of this. But a lot of these things, I will focus more on your interpretation and less on actual calculation. So a lot of these things I'll give you the numbers and ask you to interpret it.